afternoon, everyone. My name is Jennifer Dill. I'm a faculty member here in the School of Urban Studies and Planning and director of OTREC. And along with my colleague, Professor Figliosi, we help organize this weekly transportation seminar. For those of you who may be new to the seminar, I want to let you know that we do webcast it live, and also it gets archived. Because we are webcasting, we use these microphones. It's not projecting my voice, it's so people on the web can hear. So when we get to the point where you can ask questions, we'd like you to use the microphones that are on most of the tables. You need to hold the touch button, keep the red light lit while you're asking the question so the people on the web can hear it. If for some reason the microphone is non-existent or doesn't work, one of us will come with the nice portable mic to make sure your question is heard by everyone on the web. So without further ado, I'm going to introduce our speaker for the day. I'm going to do it in a little different order than I've been given, because I think the most important thing about Peter Bosa is that he is an alum of the Masters of Urban and Regional Planning program here at PSU. We were lucky enough to have him as a student a few years ago. So he's currently a transportation modeler at I am very tongue-tied today. Sorry. Portland Metro's Transportation Research and Modeling Services Program. He has over 6 years of experience in designing and applying transportation models for regional and corridor level forecasting of travel behavior, vehicle emissions for air quality analyses, and applications for the Federal Transit Administration's New Starts program. He's one of the primary developers behind Metro's Regional Dynamic Traffic Assignment Initiative. And while he was here at PSU, he worked in the Intelligent Transportation Systems Lab as a graduate student assistant. Without further ado, Peter Bosa.
Thank you, Jennifer, and thank you for having me. As Jennifer mentioned, I am an alum of the MERP program, and I worked in the ITS lab, and so I actually took this class for credit and then audited it many times since then for professional and personal interest. So I'm very excited to be here today. I work for Metro, which, among other things, is the region's MPO, Metropolitan Planning Organization. That's the facet that I'm most involved with. We are responsible, my group is responsible for developing, maintaining, and applying the transportation modeling tools used by Metro in their long-range transportation planning processes. And today I want to talk about one of those tools in particular. It's a tool we've been developing for the last few years. We're really excited about it. We think it's going to give us a lot more information and data for use in planning and policy decision making. It's called DTA, Dynamic Traffic Assignment, and let's just dive right in. So I'm going to spend a little bit of time talking about just generally what we do at Metro in terms of transportation modeling, what we're interested in achieving with our modeling. And then I'm going to get in a little more specific about assignment tools and various resolutions of those tools. There's macroscopic, represented by our static assignments. There's microscopic, or microsimulations. And then mesoscopic models, which dynamic traffic assignment is a part of. And that's really what we're here to talk about today. So once again, Metro is an MPO, Metropolitan Planning Organization, for the Portland metro area. It's a federally required agency for populations over 50,000 with the responsibility of coordinating transportation planning for the entire region. So as you can imagine, a large region like Portland has many jurisdictions in it. There's 3 counties on the Oregon side, Clackamas, Multnomah, and Washington, about 24 cities, and even state agencies. So Metro's responsibility as an MPO is really tying together all the transportation planning among these various jurisdictions. Our plans generally fall into 2 types. There's long-range system plans, such as our regional transportation plan. These are plans that basically look 20 or 30 years out. They try to identify major transportation projects and funding sources for those projects, and we're required both by the federal and state governments to update those regularly. We also help local jurisdictions with their transportation system plans. So these are similar types of plans looking at transportation projects, but more locally focused. And oftentimes, if the jurisdiction is big enough or if they have a lot of transportation plans that are really going to impact travel demand, we'll be called in to do a lot of the modeling for those jurisdictions. We also do corridor level studies. So these are actually, I would say they're more implementation type plans. So examples are major infrastructure projects that are imminent. So max line extensions. Metro plays a big part in doing the modeling for those. Roadway improvements, we do a lot of modeling for major highway facilities that are planned in the region. And we also have started to develop non-motorized models, so looking at bike and pedestrian networks for the region. We also look at air conformity analysis. So we're required by the EPA and Oregon's Department of Environmental Quality to ensure that vehicle emissions remain below certain thresholds for various toxins and particulate matter. And we do some greenhouse gas work as well with our transportation models. So just a very rough overview of what we do at TRMS. Our main tool is our travel demand models. And these are actually a set of models kind of all tied together. They feed information into one another, and they run iteratively to evaluate big scenarios in our transportation plans. The typical process that we use is a 4-step modeling process. And basically what this entails is taking a set of inputs, usually socioeconomic population data, usually by household. It looks at things like household income, size of the household, number of workers in the household. And these can be projections into the future. We also look at projected employment data for the region. So what types of jobs are there going to be, where are those jobs going to be located. And we look at other things like the transportation system network, various costs associated with that network, like transit fares or parking costs, and some urban form variables like urban density, clusters of retail sectors, et cetera. And with that information, we generate a set of trips. This is a forecasted set of trips for the region. That's our generation step. Once we've generated those trips, we determine where are those trips going to go. That's our destination choice. How are those trips going to move through the region? Once we've determined where those trips are going to go, we look at mode choice. How are those trips going to get there? Are they going to drive in a car? Are they going to ride as a passenger in a car? Are they going to take transit? Are they going to walk? Are they going to bike? Finally, once we've determined how people are going to get places and what mode they're going to take, we develop a set of trip tables that represent those trips, and we do a route choice assignment. And that's really what we're focusing on today, is this last step, the assignment step. And in particular, assignment usually is vehicle, so SOV, single occupancy vehicle, HOV, and trucks, transit or bike and ped. We're really focused just with the vehicles right now for DTA. So in the past, some of the modeling questions have been, what are the volumes on our system? Where are people going? How does the system look? If you're looking at a specific corridor, you might want to set some sort of existing condition benchmark and see how does that change as you go into the future. How do volumes change as you evaluate different scenarios? From our model, we were able to do that pretty easily, from our static models, pull out volumes, average speeds, and travel times through the corridor. The other thing that we look at are volume to capacity ratio. So how much traffic is using the system relative to the design capacity of the system. And in areas where that demand is really pushing the limits of the capacity, we looked at that and said, okay, those look like trouble spots. Let's focus in on those areas and see what we can do. And oftentimes, the way you dealt with that was to build your way out of congestion. And I don't just mean like building extra roadway capacity or highways, which certainly is one alternative, but also building alternatives such as transit systems that might help alleviate some of the congestion in that area. However, as we move forward into time, especially as we start projecting out into like the year 2035, 2030, we're noticing that our networks are becoming more and more congested. We're at a point now where we've kind of reached the tipping point where we're not going to be able to build our way out of this congestion any longer. It's not enough to just look at a location and say, okay, that's pretty bad, but we can add a couple turn lanes there and we'll fix the problem. Instead, we have to come to terms that we're going to have to live with congestion in this area. So the emphasis is now turning towards more better management of the existing system. So how can we make that congestion livable? How can we deal with that? And in order to answer those questions, you need to have information about where is the congestion occurring, what kinds of bottlenecks are occurring, how much of your facility is impacted by those bottlenecks, and what's the duration of congestion. If it's only half an hour in the peak period, maybe that's not so bad. We can live with that. But if it's 5 hours or if it's 12 hours, that might require some different thinking to deal with them. There's also this question of reliability. So reliability is kind of one of those terms that it's hard to pin down exactly what people mean by it. What I mean when I talk about reliability is consistency. So for example, if you are traveling between point A and point B, and your average travel time is 20 minutes, okay, that tells you a little bit about what that travel experience is like. But what if that 20 minutes means that one day it was 30 minutes and the other day it was 10 minutes? That doesn't, you have a high degree of variability there. And that's different than if your travel time was maybe 22 minutes on average, but it was 24 minutes one day and 20 minutes another day. There's much less variability there. And that kind of information is important because people make decisions about travel based on that reliability, based on what they perceive their travel experience will be. So our current tools right now are not, there's not enough temporal detail to actually capture congestion at a regional scale. And they're not capable of providing operational level detail at a regional scale. And I'm talking about the macro and micro assignments. And so this requires the development of new tools. So now I'm going to dive in a little bit and just give a very general overview of the different assignment resolutions. So macro assignments are deterministic models based on the relationships of speed and density on a traffic network. By deterministic, I mean if you put in the same set of inputs and you run your model 100 times, you're going to get the same solution set every single time. There is a single solution. As opposed to stochastic, where you actually introduce in probability and randomness, you run your model 100 times, you'll actually get slight deviations in your solution set every time. And that'll be important. That'll become more clear as we move further through the presentation. Furthermore, trips are aggregated into time periods by zone pair. We're not simulating individual vehicles with a microsimulation or with a macro simulation or like a static assignment. So what we typically model at Metro is a PM 2-hour peak period, 4 to 6 p.m. Generally, that is the highest demand period for our system. And so we look at the total number of trips that occur within that 2-hour period, not individual trips. So we can't distinguish between trips that happen at 4 o'clock versus 4:30 versus 5:30, et cetera. We do distinguish between vehicle classes. So we have SOV, HOV, and truck classes. But because all the trips are aggregated, those classes are homogeneous. So all SOVs behave the same. All HOVs behave the same. All trucks behave the same.
Peter, just in case, you might want to define SOV and HOV.
Okay, yeah, I'm sorry about that. SOV is single occupancy vehicle, so it's a single person sitting in their car. HOV is high occupancy vehicle, so that's 2 or more people. We define HOV as 2 or more people in this region. Other regions define it as 3 or more, et cetera. So if you have a passenger in your car, that's HOV. So basically what we have is our region, which in our model actually includes Clark County and Washington, because even though that's not part of Metro's jurisdiction, Clark County plays a very important role on our transportation network. So our region is currently broken into about 2,100 transportation analysis zones, or TAZs. And what we're doing is we're analyzing the trips between each one of these zones. Zones tend to be more dense, where population and employment are more dense, and they tend to be bigger in very rural areas. Once we run our model, we create trips that are put into matrices that represent every zone-to-zone movement in our system. So if we have 2,100 zones, there's a matrix that's 2,100 by 2,100. That's 4.4 million zone pairs. So we're basically populating these huge matrices that show all the trips between these various zone pairs for each of our vehicle classes. So here we have zone 1 to zone 1. Those are internal trips, 54 SOV trips in a 2-hour period, 4 to 6 p.m. From zone 1 to zone 2, 63, zone 1 to zone 3, 19, so on. On top of our zones, we have a representative transportation network overlaid. This network does not contain every single facility in the region, so we don't have most of the local streets, but we do have major facilities like freeways, arterials, major and minor, and major collectors. We also have the full transit network overlaid on top of this. So this is my attempt at trying to explain in 2 minutes what a static assignment is doing. Let's say we have 2 zones, zone 1 and zone 2, or let's just say 2 points, not necessarily zones. Zone 1 and zone 2. And between those 2 points, we have a demand for a time period, 2,500 trips that want to occur between zone 1 and zone 2. There's 2 routes that connect these 2 zones. We have link A here, which has a capacity of about 1,200. Its design capacity is to handle about 1,200 vehicles per hour. We have, and it's a bit shorter. We have link B, which is a bit longer, a bit more circuitous, but it has a design capacity of 1,800. So maybe it has fewer signals on it. Maybe it has a left-hand turn lane, so vehicles making left-hand turns can get out of the straight-through moving traffic. We establish a relationship between these types of links and the way that their travel times degrade as volume increases across those links. So links that have lower capacities, as the volume tends to increase on those links, travel time increases faster than link B here, where it's designed to handle more traffic. So we have volume increasing here, we have travel time increasing here. When we start out, very little volume is on the network right here. Link A is faster than link B. However, at some point here, we find that as the volumes have increased, link A starts to degrade faster than link B. And eventually, at this point, where we see that link A is much faster than link B for a given volume, right in here. So I know that this can be complex. Basically, what happens is the assignment algorithms shuffle trips back and forth between your various routes until all the trips have been assigned. And so that all the assigned trips, so we have 2,500 trips here, so that no trip can switch to another path without incurring additional delay. So all trips between the 2 zone pairs have the same travel time, essentially, which in this hypothetical is 15 minutes. If, say, 100 trips were to move from link B here, so the volume went down to 1,400. If we follow this curve down to here, we'd see that the travel time would actually be improved. But those trips need to go somewhere. So they'd go to link A here, and the volume would increase, and so would the travel time. So basically, we're trying to reach equilibrium, where all of our trips are assigned, and they all experience roughly the same travel time. Of course, our network is much more complicated than just two routes between 2 locations. And this is just one example. So this is one zone pair of the 4.4 million from downtown Portland to downtown Gresham, and it has 17 different paths associated with it. They all tend to have generally the same travel time. There is some variation there, but for the most part, they're about the same travel time. But the really important thing that I want to impress on you here is that in our static assignment, we have all these different paths available to our trips. And so if something happens to one of these paths, trips can deviate to other paths. So if congestion was to occur here, we might see these trips going to one of these other paths. Likewise, if we were to make an improvement right here and improve the travel time, we would see trips moving from these other paths to this link. And that route choice, that route finding capability is probably the most important thing to keep in mind from the static assignments. Now, there are some idiosyncrasies with static assignments. The main one is that they will assign total demand in your time period regardless of whether or not that demand exceeds the design capacity. So in this case, this is exactly like the other one, except I've increased the demand to 4,000. However, our hourly capacity is 1,800 here and 1,200 here. It's only 3,000. And now our travel time is 75 minutes at equilibrium. Well, if we were to look at the output from this model, we would see all of those trips, 4,000, occurring within the 1 hour time period. However, the true travel time is 75 minutes. We know that a lot of these trips would not be able to complete their journey in that 1 hour time period. And this is an issue with static assignments. Because they're not constrained, they don't allow for queuing, congestion to build up on your network. And so sometimes they can give you results that are not intuitive. Here's an example of what happens. And so I know the legends aren't very legible here, but on this side we have volume to capacity ratio. So this is the demand relative to the capacity. And the reds are where they exceed 1. So that means that there's more demand on the network than the network was actually designed to handle. And this is what happens in very congested conditions on our networks with static assignments. We have a lot of red through here on our freeways, but it doesn't tell us anything about where did the congestion begin. You actually can't tell if this entire link here is congested or if it's just really congested right here. And you don't know when it began. So if this is a 2-hour assignment, I don't know if the congestion began right at the beginning of the assignment or at the end. It's just assumed that the entire assignment has the same characteristics. On this side, we have speed. And there's actually not even a legend, didn't even show. Oh, there it is. OK, so we have, if we just, what I want you to get from this is that the speeds are the same for the entire time period. So it's average speed, essentially. And here it's showing orange, which is like 20 miles per hour. So it's saying that for the entire assignment period, in this case it was a 2-hour assignment, the average speed was 20 miles per hour for everybody going across there. And we know that's not the case. We know that there's variation in travel times over that 2-hour period. 4 o'clock is going to look a lot different than 5:30 or 6 o'clock. OK, so again, just to reiterate, the pros of the macro simulation is route choice capability. It's fully integrated with our regional travel demand model. So there's very little work needed for us to pull results out and feed them back into our model. It's computationally very fast, and it works well at a regional scale. Typical types of outputs we've gone over. The cons are that you get those volume to capacity ratios that exceed 1. There's no queuing because of that. And you also have no temporal dimension to your data, so you're not able to analyze bottlenecks or queuing. And again, you're looking at aggregate trip tables. You're not looking at individual vehicles. So you can't produce these queue formation spillback profiles. You can't measure the length, duration of congestion, and doing other things like looking at individual profiles to get really precise emissions estimations. So then we have microsimulations at the other end of the spectrum. And these are the stochastic models, so there's actually variability and probability entered into them. And they're looking at the individual level. So you're actually modeling individual vehicles. You're looking at acceleration, deceleration of those vehicles. You look at the merging of vehicles on a lane-to-lane basis. You can have things like politeness, like how likely am I to slow down to let somebody merge in front of me. You can look at things like gap acceptance. How much time do I need before I make a left-hand turn across incoming traffic lanes? And they're really great for evaluating operational projects. So looking at ramps or auxiliary lanes on your system, looking at intersections, traffic signals, determining decision points. Where should I put signage on my system to alert drivers of an upcoming like off-ramp or merge area. Because you are simulating individual vehicles and you're actually doing it in very, very small increments of time, you're getting a continuous stream of data. So you're gaining a temporal aspect dimension to your data. And the vehicles are confined to your roadway capacity. So once the demand of vehicles, the flow of vehicles on your roadway reach a critical point, you begin to see things like queues build up, congestion, you get spillback, and you can measure that on your system. So here's some examples of some microsimulations. The top is basically looks like an interchange off a major freeway. You can actually see the individual vehicles here. These would be moving through time if that was running. You have stop areas. And then here's just a really simple demonstration of a microsimulation. It's a roundabout. And you can see little vehicles come up to the stop area, and they'll decide whether they're going to wait or pull out in front of another car. So there's a lot of variables you can set for these microsimulations. And so pulling out that temporal temporal dimension of data is what I want to impress on you is the important part of the microsimulation. And this is my attempt to show you how that data can be used. So some of you might be familiar with these diagrams. Many of you probably not. And they can be a bit confusing when you first see them, but there's an incredible amount of data in these space-time diagrams. They're also sometimes referred to as brain scans. What we have on the y-axis is a corridor. Okay, so this is actually I-5 with this is the Columbia River Bridge right here, and this would be where I-5 meets 205. So you actually have vehicles traveling in this direction along I-5. The x-axis is your time. So as you move from left to right, you're moving forward in time. And then the colors represent your speed. Colder colors are faster speeds. Warmer colors like yellows and oranges and reds represents congestion or slower speeds. So the way you interpret this is that at the beginning of your simulation, and this goes from 1 o'clock to 8 p.m. Beginning from 1 to about 2:30, speeds are pretty fast through your entire corridor as cars are moving this way. By about 2:45, we start to see some yellows occurring at the I-5 bridge. And as we continue moving through time, those warm colors start spilling back. We're actually seeing congestion forming on our system. And that's our Q buildup. And it continues to spill back all the way from the I-5 bridge, and here it's showing it's going all the way to Capitol Highway. That's almost 12 miles on our system here, to about 5:30. And then it begins to, as the peak of the rush hour begins to subside, we see some dissipation here. So what's great about this diagram is that we can actually see how much of our system is impacted by congestion. We can see where that congestion began, and we can actually measure how long did that congestion last. In this case, I would say it lasted almost 2, 3, 4, like 4.5 hours. And this, by the way, is from actual loop detector data. This is sensors in the roadway collecting real-time speed information from cars traveling across. So this is real world. And here's a microsimulation of that same corridor, and it's actually capturing the same data. Again, vehicles are traveling in this direction. This is time in this direction. We see a lot of congestion at the Columbia River, spilling back, and then eventually dissipating. So that's a space-time diagram, and we're going to be coming back to more of those. Okay, so one of the issues with microsimulations is the fact that oftentimes vehicle trajectories are preset in them. So they don't have true route choice finding capability. So in this example, we have our little roundabout. A vehicle coming in from gate A, so entering a gate A, going to gate 4 has a set trajectory. This is the route that vehicle must take. And then the microsimulation might determine, okay, is it going to wait for this car to come around before it pulls out into traffic? And will it slow down and let these vehicles pull out, et cetera? So it's determining how the vehicle behaves, but the trajectory is set. Now, if something were to happen here, if a lot of vehicles pulled out and this became completely congested and maybe gridlocked, this vehicle still has to go this way. So it'll just have to wait for that to clear out. Where in real life, if this was bad enough, that vehicle might decide, oh, well, I'll take this route instead. I'll go around that. Well, that can't happen oftentimes in microsimulations. One, sometimes they don't have that route finding capability. And two, because microsimulations are so complex, often they're designed at there's a small geographical area, so it doesn't capture all the parallel routes. And as a result, you don't have other routes that vehicles can take. So again, microsimulations are very fast, lots of detail. We like their operational characteristics, and we like their temporal dimensions. They're great for producing space-time diagrams, and individual vehicle trajectories, and they're great for doing queue analysis. The cons are that they're very time-consuming to develop and calibrate, and because they're time-consuming, they can also be very expensive. They're computationally very intensive because you're measuring every one of these vehicles in almost sub-second time frames. The vehicle paths are fixed, as we pointed out, so what that can oftentimes lead to is an overestimation of delay through a network if vehicles aren't allowed to choose different alternative paths, and you can underestimate speeds through a corridor if you haven't calibrated your network properly. So what do? We have these benefits, the route finding capability of static assignments, but the thank you. We have the route finding capability of our static assignments and our temporal profile of our micro assignments, and we end up with DTA here. So DTAs are great because they model large subareas, or we've even run our entire regional network in them before. They maintain route choice capability of the static assignment of the macro models, but they also allow you to simulate individual vehicles continuously through time like the micro models. And the way they do that is you don't have as much behavioral detail associated with your vehicles in the DTA. And they can be either deterministic or stochastic. Vehicles are limited to the carrying capacity of your network, so you do get queue formation, you do get spillback, and you can begin to measure those things. You can also begin to measure things like how trip characteristics change through time. So my trip from Portland to Oregon City when I drive home at night is different at 4 o'clock than at 4:30, which is much different than at 5:15. And you can begin to measure those differences with the Mesosimulations or the DTA. So here's an example of some data comparison between DTA static assignment and actually real-world data. So the blue line is portal data, which is, again, roadway sensor data in our highway network that's collecting real-time information from vehicles traveling across it. This is at a location on US 26. And this is from 3 p.m. to 6 p.m. And what we're seeing here is that as the peak period progresses, we're getting more and more traffic on our system until about 5:30 when it drops off precipitously right here. The flow rate drops off at this location. And what that indicates, actually I've investigated this, there's actually a bottleneck that's like down here that spills back, and eventually by 5:30 there's congestion from that bottleneck at this point, and so fewer vehicles can get through, and we're seeing that in the flow rate right here. Well, the red line, our DTA, does a fairly good job of matching that trend. Not only the increasing trend of increasing flow rate as the peak period progresses, but then it's capturing actually the bottleneck spillback to this location. If you look at the black line, which is our static assignment results, you just get an average flow rate for the entire time period. It's actually lower than what the real world or the DTA data show, and it tells you nothing about a bottleneck influence in this particular area. Here's an example. This is travel time through a corridor. So this is I-5 northbound from the Rose Corridor up just across the Columbia River Bridge. This is from 4 to 6 p.m. And what we're seeing is how that travel time changes if you're driving that entire corridor through time. So in our static assignment, we just get an average. It's basically 22 and a half, 23 minutes for the entire 2-hour time period from 4 to 6 p.m. Whereas in the DTA, we see that at 4 p.m., our travel time is 19 minutes. By 5 p.m., we're up to 23 minutes. And by 5:30, we're up to 27 minutes. So there's a big difference in travel time experience across that time frame. And this much more closely matches what's happening in the real world. Okay, so what I'm trying to do with this is show you how the DTA is working. I have two images side by side. The image on the left actually contains lane queues. And so these red areas here, that is the formation of stopped traffic congestion. And you'll see as we advance through time how those build and dissipate. On the right, it's the same network, it's the same data, but instead we're capturing speed. So reds are really slow speeds, blues are faster speeds. So I'm just going to progress this through time and point out some things. Okay, so as we move through time here, what we see now is long queues, slow speeds, and what in the next few slides as I progress this, these queues are going to build. We're going to see a lot of congestion and spill back here, and the result is going to be a lot slower speeds here. And now it's going to start to dissipate. And then now there's a queue down here. This is going to dissipate as I move through future. So that's really exciting for us. In the past, we just have a single snapshot of that network, and we just have to make a bunch of assumptions about where congestion might be occurring on it. This, we can actually see where the congestion is occurring, when does it actually begin, when does it end. As you can see, it's very dynamic. What I've done here is I've taken those same images and I've done a space-time diagram with those. So this is similar to the other images, except this time we're traveling southbound, so it's these lanes right here, southbound. So the direction is here. This is where our congestion is occurring and spilling back to here and then dissipating. And as I move forward through time, each one of these corresponds with a slice here. You can see that right now we've got long queues, lots of congestion. We're capturing that here and here. And I'll continue moving through time. It's dissipating. And what's great about this is, again, with our model now, we've been able to capture where the bottlenecks, how much of the facility is impacted, and how long does that last. So we have a really good, almost a three-dimensional level of detail as to what's happening on our system. I'm going to skip these, and I'll get to this. So this is dealing with the stochasticity that I mentioned before, little bits of randomness in your assignments. And what this randomness allows you to do is replicate actually real-world experiences. So I know from my own personal experience, if I drive at home on Monday at 5 p.m., I get one travel time. If I do it the following Monday, I'm going to get a different travel time. If I do it the following Monday, I'm going to get an even different travel time. There's little variations in my driving experience every single day. And that's just due to driver behavior. You know, all these things begin to add upon each other, and little variations in driver behavior and signal timing, when you get to a signal, etc., impacts how long your trip is. So what we can do is we can actually take that information and we can start to build reliability. How much variability is there between day-to-day travel times? So what I have here are two scenarios. Again, we're going to look at travel times on US 26 westbound from downtown, like out to Cornelius Pass Road. It's a pretty long corridor. And at this location, we're changing the network. So here we have 3 lanes. We have an off-ramp. And this lane is dropped in between the off-ramp and the following on-ramp. In this situation, I've just continued that 3rd lane all the way through. So it's a pretty simple demonstration. So what I do is I run the model 20 times so I can get a statistically significant number of solutions. And I plot the travel time for each one of those model runs. And again, we're looking at 4 to 6 p.m. This is your travel time through the corridor. So at 4 p.m. with this red line, it's about 22 minutes. By 5:30, that travel time is increased to like 30 minutes. I've plotted the 5th and 95th percentiles from those 20 runs that I've done. And here I've actually shaded the area between those percentiles. And what you can see here is areas where the 5th and 95th are really close together, there's very little variability, meaning that it's highly reliable right there. You're not going to see a lot of variability in your day-to-day travel time. Whereas here, there's a lot more variability. You go anywhere from 26 minutes all the way up to 32, 33 minutes. So there's a big difference. And a lot of that is due to, as congestion builds, you get much less reliability on your network. Well, now I've added this lane in here, and lo and behold, my variability has decreased for most of my time period. I've actually improved reliability through the corridor just by adding that lane here. I've actually improved reliability through the entire corridor. And if I map it with the previous scenario, you can see it's much faster the entire time period, but it's also much more reliable from about 4:30 all the way to about 5:30. At 5:30, I would argue that it's less reliable. There's much more variability in the new scenario than there was in the old scenario, but it doesn't matter. Your 95th percentile travel time is still better than your worst travel time here is still better than your best travel time in the old scenario. So those are just some of the examples of how we can use DTA to start asking different questions about our transportation network. Of course, there's this idea of multiple resolution modeling, where you don't just use a single resolution of model. You use the resolution that's most appropriate for your task at hand. So we're going to continue using static assignments for use with our travel demand models. And microsimulations are still going to be used for very high detail operational design problems. But in the meantime, if we've got these questions that aren't quite operational, like how big should our merge lane be, but we still want to like get information about, well, when's congestion forming and how long is it lasting, the DTA is a perfect tool for that. So moving forward, we're going to start applying this in our corridor level studies. We're going to begin integrating it with some of the emission software that's out there so that we can get very high quality, precise greenhouse gas estimates and emissions estimates. Eventually, we will be developing a transit and bike PED component to DTA. Once we do that, we'll be able to integrate DTA into our larger model framework. We are developing more advanced models. We have an activity-based model coming out soon in the next couple years. That's soon to me. And we'll actually be modeling individuals, not just in their vehicles, but in their day-to-day choices even. And eventually, DTA, I say every assignment here, but I mean the DTA may replace the static assignments at some point once we get some of these other components added in. And with that, I'm happy to take questions. Sure, back there.
Oh, hold on 1 second. It's working, so here we go.
Yeah, I was just wondering how, with all this modeling and information, kind of like what's the time period between solving and implementing, I guess. How does that process work? Does that make sense? Like you find a big congestion area, but what do you actually,
Sure.
How do you make those adjustments?
Sure. So I guess there's two ways in which you can use this data. You can use it at an operational level. So what are things that we can do in the short to medium term to alleviate that? And that might be things like adjusting ramp meter rates or signal timing on parallel facilities so that you can increase route alternatives for travelers. And then there's this question of like looking at long-range scenarios, these planning alternatives. So looking at packages of projects together and how they impact the system. At Metro, we do some of the operational stuff, but really when we're doing our planning, we're looking more at the long term, medium to long term. So I don't think it necessarily speeds up the planning process. I think it gives us additional information to consider during the planning process, if that makes sense. And then that might actually impact the types of projects that go into our future plans based on that. Sure, right here.
As transportation engineers, we've traditionally thought that you can build yourself out of congestion, but we've become we've become more aware that it also increases demand as you increase capacity. And so I was curious, in your models, do you account for the fact that when you increase the capacity of a certain section, that there will be extra demand as people learn that the travel time is now reduced a little bit?
Sure, absolutely. So our models are iterative. We never just run them once. So if we increase the capacity in a certain location, what happens is the next time we run the model, we're going to see a lot of people shifting their trips to that particular section. And sometimes too many trips go to that location, right? And it actually makes it worse because so many people have gone there. But if we iterate over time, what happens is there's kind of an equilibrium. Some of those trips will remain on that new section. Other trips will deviate away from there. And so when we model, we're not doing like one shot, a snapshot like, okay, we're opening up this facility, this brand new facility, adding capacity. How's it going to look the day after we open it up? What we're looking at are long-term trends. So, okay, we've added capacity. Once the system stabilizes, once people get used to that additional capacity, how's the system look then? So, yeah, we are accounting for that. Now, there's also questions about how does that impact land use and whatnot, and that's a larger question outside of the context of this. But we do actually integrate our models with land use models, so we do see changes to people's behavior in that sense. Like they'll go to different places to shop, or they might over time actually choose different places to work or live. Actually, you had a question before.
Yeah, you talked about long-term projections. Where in the metro area do you see like the highest demand within the next 20 years?
The entire area, actually. So there's two parts to that. Obviously, the Portland metropolitan area will continue to be the main core of the region is going to be very high demand. But obviously, as we move into the future, a lot of that growth happens in the periphery, and those areas are going to see the greatest change in demand. I haven't looked at the land use projections for the latest. Actually, Metro is going through and reforecasting land use projections, and they'll be adopting new land use projections for out to 2035 sometime this spring. But it's going to be considerably different than what we've done in the past. It's going to take into account our urban and rural reserves that have recently been the process that Metro went through in the last year or so. It'll take into account UGB expansions, et cetera. So we're going to see a lot of growth in the periphery, definitely. And we're going to need a lot of transportation infrastructure in that area to handle that growth. Yes, right here.
I'm curious how the collection of real-time data affects how you model, how you do your modeling, and if there have been any recent advances in the collection of real-time data that has significantly affected your modeling.
Absolutely, actually. In terms of modeling, the great thing about real-time data is it provides a baseline for your existing conditions, so you can calibrate your models to that. If your model can't replicate what's happening in real time, then it's not going to do a good job of forecasting what's going to happen in the future. So the first step when you develop a model is to calibrate it to existing data. Now, we're very fortunate in this region. We have a wonderful resource, and that's the Portal system, which is an archive of road sensor data that covers the entire freeway system here. And being able to pull upon that data to look at how our models are calibrated is really important. Those space-time diagrams I showed at the onset, where we looked at the I-5 bridge and the spillback, we have that temporal dimension. That provides us a whole new level of data to calibrate something like our DTA, where we also have a temporal dimension. In terms of new sources of data, with the prevalence of GPS in vehicles now, there's actually third-party proprietors out there who have calculated travel times along entire corridors with this GPS data. So in the past, I don't know if I... So let's just say in this image, we have a sensor right here at this location. That sensor is great for telling us what's happening exactly at that location. But it doesn't really tell us what's happening through the entire corridor. Even if you have a lot of sensors here, unless they're spaced closely together, it's difficult sometimes to pick up exactly what's happening in your corridor. I actually, oops, well, I turned it off. I actually have an image right here, actually, where we've taken our DTA data, that's the red line right here, and compared it against GPS data. This is from INREX. And this is for entire travel time through this corridor right in here. So what's great about this data is that it gives us continuous data for a continuous corridor.
Yeah. You mentioned in the future developing this similar modeling for transit and ped bike infrastructure, and I'm just wondering what kind of impacts the kind of simplification of the behavioral variability would have in that setting, and if it would have more of an impact. I don't know if there's more variability in ped bike behavior than in motor vehicle behavior.
Sure. Let me just start by saying that the ped bike stuff, well, I think transit is probably the next step, and that's actually still being researched right now. Outside of our agency, that's still at almost the academic level. And the way that that'll be represented at DTA is not only transit vehicles moving differently through time. So buses being stuck in congestion, moving differently through time, kind of queuing up and then dissipating. That'll impact your transit decisions. Well, am I going to wait for this bus or am I going to take that other bus? So that's the next important role, is getting transit. In terms of bike ped, I'm probably not the right person to discuss that. The way that we currently model bikes and pedestrians, it's different than how we model traffic. We don't really look at congestion when we model bike ped. But certainly if there's a lot of congestion, we could see mode choices. We could see people moving away from their vehicles and even from transit and going more towards bike and pedestrian facilities, especially if there's additional infrastructure. Sure, right there.
To what capacity does your office make recommendations versus analyzing data or figuring out like particular idiosyncrasies with lanes or whatnot? Like, how do you come to the point of being like, this is a new corridor we could look at, or here's a new project we could recommend? Does your office do that, or do you provide that, I guess, to someone else to make those decisions?
It's usually the planners are actually the ones who are working with the policymakers to determine that. We do advise them in terms of the technical aspects of the models, but we try to stay as independent as possible. Our preference is to just take a set of inputs, make sure that they're reasonable, and produce a set of outputs, and then again make sure that they're reasonable given the set of inputs. And then we'll pass that on to the planners and the policymakers, and they can catch the flack and for that. Right here.
With regard to the stochastic modeling and reliability, questions: one, what dimensions of the DTA are impacted by the random seed? And two, how well has that been validated for either day-to-day variability or inter-vehicle variability on a given day?
Well, okay, so the day-to-day variability we can actually start to derive from the INREX data, because there's so much data there that they actually have statistics broken out. This is your average travel time, but this is your variance. So we can begin to compare against that. In terms of the random number seed, for those who don't know, is what's used to, it's basically like it basically is used to determine whether or not you make one decision, if your probability is higher or lower to make a decision. In some of our models, in the Dynasty model that I showed those reliability plots from, it's used to determine exactly when a vehicle starts its trip. So we say, okay, the vehicle is going to start its trip between 4 and 4:15. The random number seed will say, okay, it's actually going to start at exactly 4:01 or 4:02. The other place that it's used is in when a vehicle comes upon an intersection and there's a light there, a signal. If that signal turns yellow, the random number seed will be used to determine whether or not that vehicle goes through the signal or will stop. The other thing that random number seed can be used for is that gap acceptance. So if I make a left-hand turn, do I need a second and a half of space before I make that turn? Do I want 2 seconds of space? Do I want 3 seconds? So those are just a few of the areas where it's used.
From the web, and there are two. One is in terms of calibration and variability. The question is, as variability increases, how much more complicated it is to get the calibration right in terms of representing that stochasticity in the network. And then there was another part of the question. As people are getting more cell phones and more real-time information and online routing, like real-time, how this can, is currently has the capability of reflecting that, or is something that you think you're going to be adding, or?
Okay, so the first question was...
So it's the variability in the
okay,
travel times.
Okay, so calibrating to the variability, and then the second one is integrating more real-time data into it. Well, I'll answer the second question first. I think that we just calibrate to an existing year, and then once we've calibrated to that, then we move forward and do future year projections, and that's really where our interest is in applying these tools. So obviously, as we have more real-time data, as we look at our corridors, different corridors, we can calibrate more precisely to those corridors. Right now, our main emphasis, and maybe this starts to answer the first question, is just calibrating our freeways, getting our freeway system as dialed in as possible, and not worrying so much about the arterial system. When you're modeling at a regional level, if you try and get every single facility fully calibrated, it's a Herculean effort. You'll never be able to accomplish it. It's just not feasible. So right now, we're focused on matching the freeway system. In matching the freeway system, what we really want to match we don't want to match. I mean, this is great right here. We feel like we've done a pretty good job of matching the speed profiles. Here's speed and travel time profiles. We'd be very happy if every single freeway looked exactly like this. We don't expect it to match as well. What we want to capture really are trends. So we want to see the peak periods showing the same type of peakedness in our model. We want to see if we do a really long simulation period. So if we do a 24-hour simulation, we want to be able to see our AM peak and our PM peak. They might not line up exactly with real data, but that's okay. We're looking more for trends at this point right now.
You mentioned that you expect that the land use model to show more development in the suburb. I see some writing in current literature that there is a movement toward urbanization. Have you heard anything like that?
I'm not familiar with that. I mean, our model is so the land use modeling for our region actually happens in a completely different department than ours. But we work closely with them because the land use is an input into our model. And we have seen, as we move out into the future, the areas that are slated for growth in our region that have been adopted into our comprehensive plans for growth are predominantly in the suburban areas. Now, obviously, there is Metro places an emphasis on infill, so there's a big call for redevelopment inside the existing urban area. And I think, depending on who you talk to, they would prefer to see that happen first. But given the number of people that we're expecting in the region and the number of jobs that will be required for those people, both for employment and shopping and et cetera, you're definitely going to have development happening in the periphery. It's just inevitable.
Thank you very much, Peter, for a great seminar. We're at 1 o'clock.
Perfect. All right. Thank you.